the same number of significant figures as my experimental data shows, then we're right there. We're bang on there. So 2.0. We can even just cross that out to show the rounding. Okay. So that gives me a lot of confidence in the accuracy of my data and the accuracy of that equation, the t equals 2 pi over square root g times square root l, as a suitable equation to model this situation. Okay. So the other thing we didn't talk about, which we need to talk about, is the intercept. This one here shows a non-zero intercept, whereas the equation actually has no intercept. And it makes sense, and this is a comment you could make in your discussion as well, that you shouldn't have an intercept, because for a pendulum of length equals 0, okay, picture your pendulum, here's your string with your pendulum bob, that length goes to 0, so your pendulum's right up there, it can't swing. So the period should be 0. Okay, so length 0 in here should be 0. Okay. If I've got a result above 0, what that means is, on my graph of period against square root length, and it runs through above 0, so we've got that non-zero intercept, that means the entire graph has been shifted up by that amount. Okay, the entire line. If my gradient is still what it should be, so the gradient is all good, but see the intercept, we don't know where that is. That's y equals mx plus c, in case you're wondering where I got those. So what that tells us, there is a systematic error, which is systematically adding a particular time period to every single measurement. Okay, so that could be that I'm consistently too slow in stopping the stopwatch, or maybe I'm consistently adding 1 whole second on every single time. Okay, so that would lift every single point plotted where they should be. They would all end up too high. That's a really important thing, and you can talk about why that is. You can say the trend is still correct, but it seems like there was a systematic error in my results, and that systematic error could come from, and you have to explain away for that period to increase in this case. So the period has increased, the only independent variable was the length, and you square root the length, but that had to somehow increase as well, because t is proportional to square root of l. So square root of l had to increase. That means your length was probably longer than it should have been. And you should speculate as to how that could come about for getting into ultimate discussion. And how that could come about is, here's your pendulum bob. Where do you measure the length from? Okay, where do you measure the length from? Most people usually just measure it to here. From the clamp up the top, okay, on the retort stand, from the clamp up the top on the retort stand to there. That's where most people measure length. But you should really measure it to the center of mass of the pendulum bob. Okay, so you might be out by a particular length every single measurement, and that is going to increase every single reading in that of that period by a factor of, remember it's over square root g, that's the constant bit, square root l. So if you're adding, say that might be ½ centimetre to every single l reading, your period is going to be out by a factor of square root 0.5 for every single reading. Hopefully you can see how that fits in. But you just need to speculate as to what it is. Even if you took into account the centre of mass, you might have got it wrong, and it's useful to discuss why that is, okay, how that could produce the effect of that systematic error. Okay, going right back to where we were at the start, just so we're there. Okay, we've covered the limitations of the experiment, how to and using the equation and the uncertainties in the equation to do that. We also have the limitations of the model that we're using to represent the real life situation. So one of the big problems with the real life situation, and I can thank one of my students this year for telling me about this, this was a good thought that they had, oops, I don't want to do that, was that in real life, a pendulum very rarely sticks to the small angle approximation that we use for simple harmonic motion. So this is talking about physics theory, which they always like to hear in these discussions. So simple harmonic motion for a pendulum is theta is approximately equal to sine theta. And in other videos it explains why that is, derivation of the pendulum formula. You can look that up under mechanics. And this is in radians. So when this condition is not held to be true, the pendulum equation over here will not, that equation doesn't hold true. Okay, but in the real life it's probably going to swing more than 10 degrees. So your equation that you've found over there, t equals 2 pi square root L plus 0.2, probably won't be that accurate because of the swinging. There's also going to be twisting and torsion in the branch, and in the like the branch itself is going to bend. There's going to be rubbing with the knot where it's tied on. There's going to be rubbing here where the knot's tied on because it's tied on with a rope. An uneven shape like this is going to be swinging in the wind. The wind's unlikely to be constant. It's possibly coming from one direction all the time, more than one of the others, so it's going to be forced simple harmonic motion. All of these different things you can apply to it, and that driving frequency may not be at the natural frequency of it. Okay, lots and lots of things you can talk about for the limitations of the model. Okay, to know whether it's an accurate representation of what we've got. Now, one way to think about it, I've written other variables, not an equation. The idea there is we've used this equation t equals 2 pi square root L upon g to model what we've got. We've considered gravity to the length as things which affect the period. But if there are other things which you can see from the real life situation that would affect the period, then you need to talk about how that hasn't been taken into account and is a big limitation. Okay, but also you don't want to get too carried away, because if your equation here is a good representation of this, you should be able to say that too. And generally, if you're within range of uncertainties for all the factors in your equation, your gradient and your intercept, you should be okay. Okay, I think I've gone on long enough, a very long video, but lots of detail there. Ask questions in the YouTube comments or email me, sam@physicslounge.org, and I'll happy to answer your questions, or maybe even make another video that clarifies this a little bit better.